The P versus NP problem is a major unsolved problem in computer science. Informally speaking, it asks whether every problem whose solution can be quickly verified by a computer can also be quickly solved by a computer. It was essentially first mentioned in a 1956 letter written by Kurt Gödel to John von Neumann. Gödel asked whether a certain NP-complete problem could be solved in quadratic or linear time. The precise statement of the P versus NP problem was introduced in 1971 by Stephen Cook in his seminal paper, The Complexity of Theorem Proving Procedures, and is considered by many to be the most important open problem in the field. It is one of the 7 Millennium Prize problems selected by the Clay Mathematics Institute to carry a $1 million prize for the first correct solution. The informal term quickly, used above, means the existence of an algorithm for the task that runs in polynomial time. The general class of questions for which some algorithm can provide an answer in polynomial time is called class P, or just P. For some questions, there is no known way to find an answer quickly, but if one is provided with information showing what the answer is, it is possible to verify the answer quickly. The class of questions for which an answer can be verified in polynomial time is called NP, which stands for non-deterministic polynomial time. Consider the subset sum problem, an example of a problem that is easy to verify, but whose answer may be difficult to compute. Given a set of integers, does some non-empty subset of them sum to 0? For instance, does a subset of the set -2, -3, 15, 14, 7, -10 add up to 0? The answer, yes, because the subset -2, -3, -10, 15 adds up to 0, can be quickly verified with 3 additions. There is no known algorithm to find such a subset in polynomial time, but such an algorithm exists if P equals NP, hence this problem is in NP but not necessarily NP. An answer to the P equals NP question would determine whether problems that can be verified in polynomial time, like the subset sum problem, can also be solved in polynomial time. If it turned out that PNP, it would mean that there are problems in NP that are harder to compute than to verify. They could not be solved in polynomial time, but the answer could be verified in polynomial time. Aside from being an important problem in computational theory, a proof either way would have profound implications for mathematics, cryptography, algorithm research, artificial intelligence, game theory, multimedia processing, philosophy, economics and many other fields. Context. The relation between the complexity classes P and NP is studied in computational complexity theory, the part of the theory of computation dealing with the resources required during computation to solve a given problem. The most common resources are time and space. In such analysis, a model of the computer for which time must be analyzed is required. Typically, such models assume that the computer is deterministic and sequential. In this theory, the class P consists of all those decision problems that can be solved on a deterministic sequential machine in an amount of time that is polynomial in the size of the input. The class NP consists of all those decision problems whose positive solutions can be verified in polynomial time given the right information, or equivalently, whose solution can be found in polynomial time on a non-deterministic machine. Clearly, PNP, arguably the biggest open question in theoretical computer science, concerns the relationship between those two classes. Is P equal to NP? In a 2002 poll of 100 researchers, 61 believed the answer to be number, 9 believed the answer is yes, and 22 were unsure. 8 believed the question may be independent of the currently accepted axioms and therefore is impossible to prove or disprove. In 2012, 10 years later, the same poll was repeated. The number of researchers who answered was 151. 126 believed the answer to be number, 12 believed the answer is yes, 5. Believe the question may be independent of the currently accepted axioms and therefore is impossible to prove or disprove. 8. Said either don't know or don't care or don't want the answer to be yes nor the problem to be resolved. Np-Complete. To attack the P equals NP question, the concept of Np-Completeness is very useful. Np-complete problems are a set of problems to each of which any other Np problem can be reduced in polynomial time, and whose solution may still be verified in polynomial time. That is, any Np problem can be transformed into any of the Np-complete problems. Informally, an Np-complete problem is an Np problem that is at least as tough as any other problem in Np. Np-hard problems are those at least as hard as Np problems, i.e., all Np problems can be reduced to them. Np-hard problems need not be in Np, i.e., they need not have solutions verifiable in polynomial time. For instance, the Boolean satisfiability problem is Np-complete by the Cook-Levin theorem, so any instance of any problem in Np can be transformed mechanically into an instance of the Boolean satisfiability problem in polynomial time. The Boolean satisfiability problem is one of many such Np-complete problems. If any Np-complete problem is in P, then it would follow that P equals Np. Unfortunately, many important problems have been shown to be Np-complete, and not a single fast algorithm for any of them is known. Based on the definition alone, it is not obvious that Np-complete problems exist. However, a trivial and contrived Np-complete problem can be formulated as follows. Given a description of a Turing machine M guaranteed to halt in polynomial time, does there exist a polynomial size input that M will accept? It is in Np because it is simple to check whether M accepts the input by simulating M. It is Np-complete because the verifier for any particular instance of a problem in Np can be encoded as a polynomial time machine M that takes the solution to be verified as input. Then the question of whether the instance is a yes or no instance is determined by whether a valid input exists. The first natural problem proven to be Np-complete was the Boolean satisfiability problem. As noted above, this is the Cook-Levin theorem. Its proof that satisfiability is Np-complete contains technical details about Turing machines as they relate to the definition of Np. However, after this problem was proved to be Np-complete, proof by reduction provided a simpler way to show that many other problems are also Np-complete, including the subset sum problem discussed earlier. Thus, a vast class of seemingly unrelated problems are all reducible to one another, and are in a sense, the same problem. Harder problems. Although it is unknown whether P equals Np, problems outside of P are known. A number of succinct problems are known to be exptime complete, because it can be shown that P exptime, these problems are outside P, and so require more than polynomial time. In fact, by the time hierarchy theorem, they cannot be solved in significantly less than exponential time. Examples include finding a perfect strategy for chess and some other board games. The problem of deciding the truth of a statement in Presburger arithmetic requires even more time. Fisher and Rabin proved in 1974 that every algorithm that decides the truth of Presburger statements has a runtime of at least for some constant c. Here, n is the length of the Presburger statement. Hence, the problem is known to need more than exponential runtime. Even more difficult are the undecidable problems, such as the halting problem. They cannot be completely solved by any algorithm, in the sense that for any particular algorithm there is at least one input for which that algorithm will not produce the right answer. It will either produce the wrong answer, finish without giving a conclusive answer, or otherwise run forever without producing any answer at all. Problems in Np not known to be Np or Np-complete. It was shown by Ladner that if Pnp then there exist problems in Np that are neither Np nor Np-complete. Such problems are called Np-intermediate problems. The graph isomorphism problem. The discrete logarithm problem and the integer factorization problem are examples of problems believed to be NP intermediate. They are some of the very few NP problems not known to be NP or to be NP complete. The graph isomorphism problem is the computational problem of determining whether two finite graphs are isomorphic. An important unsolved problem in complexity theory is whether the graph isomorphism problem is NP complete, or NP intermediate. The answer is not known, but it is believed that the problem is at least not NP complete. If graph isomorphism is NP complete, the polynomial time hierarchy collapses to its second level. Since it is widely believed that the polynomial hierarchy does not collapse to any finite level, it is believed that graph isomorphism is not NP complete. The best algorithm for this problem, due to Laszlo Babai and Eugene Lux, has runtime 2.0 for graphs with n vertices. The integer factorization problem is the computational problem of determining the prime factorization of a given integer. Phrased as a decision problem, it is the problem of deciding whether the input has a factor less than k. No efficient integer factorization algorithm is known, and this fact forms the basis of several modern cryptographic systems, such as the RSA algorithm. The integer factorization problem is in NP and in co-NP. If the problem is NP complete, the polynomial time hierarchy will collapse to its first level. The best-known algorithm for integer factorization is the general number field sieve, which takes expected time to factor an n-bit integer. However, the best-known quantum algorithm for this problem, Shor's algorithm, does run in polynomial time. Unfortunately, this fact doesn't say much about where the problem lies with respect to non-quantum complexity classes. Does P mean easy? All of the above discussion has assumed that P means easy, and not in P means hard, an assumption known as Cobham's thesis. It is a common and reasonably accurate assumption in complexity theory. However, it has some caveats. First, it is not always true in practice. A theoretical polynomial algorithm may have extremely large constant factors or exponents, thus rendering it impractical. On the other hand, even if a problem is shown to be NP-complete, and even if P-NP, there may still be effective approaches to tackling the problem in practice. There are algorithms for many NP-complete problems, such as the knapsack problem, the traveling salesman problem and the Boolean satisfiability problem, that can solve to optimality many real-world instances in reasonable time. The empirical average case complexity of such algorithms can be surprisingly low. An example is the Simplex algorithm in linear programming, which works surprisingly well in practice. Despite having exponential worst-case time complexity, it runs on par with the best-known polynomial time algorithms. Second, there are types of computations which do not conform to the Turing machine model on which P and NP are defined, such as quantum computation and randomized algorithms. Reasons to believe PNP. According to polls, many computer scientists believe that PNP. A key reason for this belief is that after decades of studying these problems, no one has been able to find a polynomial time algorithm for any of more than 3,000 important known NP-complete problems. These algorithms were sought long before the concept of Np-Completeness was even defined. Furthermore, the result P equals Np would imply many other startling results that are currently believed to be false, such as Np equals co-Np and P equals pH. It is also intuitively argued that the existence of problems that are hard to solve but for which the solutions are easy to verify matches real-world experience. If P equals NP, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Scott Harrison, Schmidt. On the other hand, some researchers believe that there is overconfidence in believing Pnp and that researchers should explore proofs to P equals Np as well. For example, in 2002 these statements were made. The main argument in favor of Pnp is the total lack of fundamental progress in the area of exhaustive search. This is, in my opinion, a very weak argument. The space of algorithms is very large and we are only at the beginning of its exploration. The resolution of Fermat's last theorem also shows that very simple questions may be settled only by very deep theories. Moshe Y. Vardi, Rice University. Being attached to a speculation is not a good guide to research planning. One should always try both directions of every problem. Prejudice has caused famous mathematicians to fail to solve famous problems whose solution was opposite to their expectations, even though they had developed all the methods required. Anil Nerode, Cornell University. Consequences of solution. One of the reasons the problem attracts so much attention is the consequences of the answer. Either direction of resolution would advance theory enormously, and perhaps have huge practical consequences as well. P equals Np. A proof that P equals Np could have stunning practical consequences. If the proof leads to efficient methods for solving some of the important problems in NP, it is also possible that a proof would not lead directly to efficient methods, perhaps if the proof is non-constructive, or the size of the bounding polynomial is too big to be efficient in practice. The consequences, both positive and negative, arise since various NP-complete problems are fundamental in many fields. Cryptography, for example, relies on certain problems being difficult. A constructive and efficient solution to an NP-complete problem such as 3SAT would break most existing crypto systems, including public key cryptography, a foundation for many modern security applications such as secure financial transactions over the Internet, and symmetric ciphers such as AES or 3DES, used for the encryption of communications data. One-way functions used in cryptographic hashing. The problem of finding a pre-image that hashes to a given value must be difficult to be useful, and ideally should require exponential time. However, if P equals Np, then finding a pre-image M can be done in polynomial time, through reduction to SAT. These would need to be modified or replaced by information theoretically secure solutions not inherently based on Pnp equivalence. On the other hand, there are enormous positive consequences that would follow from rendering tractable many currently mathematically intractable problems. For instance, many problems in operations research are NP-complete, such as some types of integer programming and the traveling salesman problem. Efficient solutions to these problems would have enormous implications for logistics. Many other important problems, such as some problems in protein structure prediction, are also NP-complete. If these problems were efficiently solvable, it could spur considerable advances in life sciences and biotechnology. But such changes may pale in significance compared to the revolution an efficient method for solving NP-complete problems would cause in mathematics itself. Gödel, in his early thoughts on computational complexity, noted that a mechanical method that could solve any problem would revolutionize mathematics. If there really were a machine with phi kn, this would have consequences of the greatest importance. Namely, it would obviously mean that in spite of the undecidability of the Entscheidungs problem, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. After all, one would simply have to choose the natural number n so large that when the machine does not deliver a result, it makes no sense to think more about the problem. Similarly, Stephen Cook says, it would transform mathematics by allowing a computer to find a formal proof of any theorem which has a proof of a reasonable length, since formal proofs can easily be recognized in polynomial time. Example problems may well include all of the CMI prize problems. Research mathematicians spend their careers trying to prove theorems, and some proofs have taken decades or even centuries to find after problems have been stated. For instance, Fermat's last theorem took over 3 centuries to prove. A method that is guaranteed to find proofs to theorems, should one exist of a reasonable size, would essentially end this struggle. Donald Knuth has stated that he has come to believe that P equals NP, but is reserved about the impact of a possible proof. I don't believe that the equality P equals NP will turn out to be helpful even if it is proved, because such a proof will almost surely be non-constructive. Pnp, a proof that showed that Pnp would lack the practical computational benefits of a proof that P equals Np, but would nevertheless represent a very significant advance in computational complexity theory and provide guidance for future research. It would allow one to show in a formal way that many common problems cannot be solved efficiently, so that the attention of researchers can be focused on partial solutions or solutions to other problems. Due to widespread belief in Pnp, much of this focusing of research has already taken place. Also, Pnp still leaves open the average case complexity of hard problems in Np. For example, it is possible that SAT requires exponential time in the worst case, but that almost all randomly selected instances of it are efficiently solvable. Russell Impagliazzo has described 5 hypothetical worlds that could result from different possible resolutions to the average case complexity. Question. These range from algorithmica, where P equals NP and problems like SAT can be solved efficiently in all instances, to cryptomania, where Pnp and generating hard instances of problems outside P is easy, with 3 intermediate possibilities reflecting different possible distributions of difficulty over instances of NP hard problems. The world where Pnp but all problems in Np are tractable in the average case is called heuristica. In the paper, a Princeton University workshop in 2009 studied the status of the 5 worlds.